Hi students, welcome to Structure Engineering Lectures and welcome to a new playlist on the design of SteelStructures as per the limited method conforming to IS 800 2007. In today's class, we shall see the design of column splices subjected to axial forces and subjected to shear forces and bending moments. Three solved problems, right? Like this. Three different problems. We'll see that elaborately. In the previous class, we have seen the design of compression member, how to find out the effective length of the columns, as well as we also examined the design of laced columns in single lacing system wherein the sections were connected toe to toe or face to face. I hope you are enjoying the discussions. In such a case, you click to like, share, subscribe, comment and turn on to our notification to our YouTube channel. Now let us see the brief profile of the speaker. That is, I, Dr. D. Rupesh Kumar, obtained my BTech in Civil Engineering from Nagarjuna University in 1994, MTech Structural Engineering from JNTU Hyderabad in 2000, and PhD in Structural Engineering from JNTU Hyderabad in 2009. Presently, I am working as a professor of Department of Civil Engineering, University College of Engineering, Osman University, Hyderabad, Telangana State. I have an experience of 27 years. After 7 years is in industry and 20 years is in teaching as well as the research at graduate and postgraduate levels. My research areas include reinforced concrete designs, steel structural designs, structural analysis, flight element analysis, earthquake engineering, bridge engineering, structural optimization. I published 45 papers in international and national journals and conferences, and organized 3 international conferences and 11 national conferences and workshops. Attended 43 workshops, visited 2 countries, delivered 13 guest lectures, edited 3 books, and supervising 14 PhD scholars and supervised 30 ME theses. I am actively involved in various consultancy works that are offered by the department and completed over 750 design proof checks and 150 designs of RCC, steel, composite, low-rise, high-rise, multi-story buildings and road and rail bridges. Right. Once we see this brief profile student, now let us see what we'll be discussing in today's class. Now, once you understood the first problem, student, now let me do the design of a splice plate for a column where they are of varying depth, right, like this, right? Therefore, now let me see the data, right? These are the data, student. This is the design of a splice for columns of different sections subjected to axial force only. The second problem is also subjected to axial force only, but they are of different sections, right? Different depths. And just now we have seen. Let's see the problem data. Here I need to provide a bearing plate, obviously, because there are different depths. I need to provide a bearing plate so that the load coming from the top column will be uniformly distributed over this bearing plate and onto the top the bottom section of the column, right, uniformly, so that there is no stress concentration. There is a purpose why we will provide the bearing plate, this bearing plate, right? Now let us see the problem, student, right? A stanchion ISHB 300 at the rate of 600 Newton per meter in the lower story of a building is joined to a stanchion of ISHB 200. This is of varying depth, please see, right, at the rate of 392.4 Newton per meter. A load of 600 kilonewton is to be transferred from top story stanchion to the bottom story, right? Design the column splice. The column ends are made flush by using the machine cut method, right? Use same previous data, Fe 410 grade steel as well as 4.6 grade bolts, right? Same previous data for the steel as well as the bolts, right? Now this is of the schematic, student, right? This is ISHB 200, right? ISHB 200, whereas the bottom column is ISHB 300. Therefore, its depth is equal to 300 mm, right? ISHB 300, whereas the top one column is ISHB 200. These are of varying depths. Therefore, now let me see if I go to this table, 46 of page number 138 of IS 800 2007, ISHB 618. Let me go to this page number 138. Let me revisit that page number 138. Yes, I am there in page number 138. ISHB 250, right? Therefore, I'll note down the relevant properties, right? Relevant properties from this, wherein I do have not here, right? Here ISHB 250, right? At a rate of, what is that, right? At a rate of ISHB 300 at a rate of 618. ISHB 300. ISHB 300 at a rate of 618. Therefore, this is ISHB 300 at a rate of 618 means 63.0 kg per meter multiplied by 9.81 will work out that those many 618 Newton per mm. Therefore, the area of the cross section is equal to 80.25 and the width, the depth is equal to 300 mm and width of the flange is equal to 250 and the thickness the thickness of the flange is equal to 10.6 and thickness of the web is equal to 9.4. That is how I have just noted down. Similarly, from the next page, I'll note down what are the properties of the ISHB 200. What are the properties of the ISHB 200, right? What is that cross section? Let me see, right? Let me see the cross section, student. There is a ISHB 200. These are the properties of ISHB 300, student. Just noted down from the IS 800, right? Similarly, for ISHB 200 at the rate of 392, let me see this, right? At the rate of 392, yes, that is 40 kg per meter. Therefore, I am noting down the properties that D is equal to 200 and BF is equal to 200 and the thickness of the flange 9 mm and thickness of the web 7.8 mm. Once I note down these properties, now I just noted all the properties here, Hence, these are the other all the properties, right? However, please see that these two columns are of different depths. I require a filler plate here, like this, right? Or let me show this schematically also, right? Like this, right? I require a filler plate. Or let me go to this schematic. Yes, these are of different depths, right? This is our ISHB 200 and this is our bottom one is ISHB 300. Therefore, I require this filler plate of green color, fill plate or filler plate. Therefore, what is the thickness of this filler plate, student? Then I'll find out this, right? Hence, that now works out. Say a value of difference of this 300 minus 200 divided by 2. Because I'll be using 50 mm filler plate here as well as 50 mm filler plate. Therefore, that 100 plus 200 is equal to 300 mm. Therefore, it will be numerically equal to the depth of that lower story column. Now, once I fix that, the next subheading is that design of the bearing plate. You please see that here the top column is resting onto the bottom column, right? If you please see that if there is no bearing plate, what will happen? Let me show this in this figure. Right? Therefore, if there is no bearing plate, what will happen is, right, if I remove this brown color bearing plate, what will happen is that the web will be having a perfect contact with the web of the bottom flange. But you please see that this flange will be leading to the load transfer on the web. Therefore, there is a stress concentration. Right? At the ends of these flanges. Therefore, stress is not uniformly distributed over the bottom cross section, but our assumption in the designs is that the web is uniformly stressed as well as the flanges are uniformly stressed. The entire cross section is uniformly stressed. Hence, we'll provide a bearing plate like this, so as to avoid that stress concentration. And the second one is to uniformly distribute the load over the bottom column through and through, right? Uniformly, right? Now, once you understood that why the bearing plate is required, student, now let us design that, right? Hence, in the designs, what now I'll do, I'm just initiating the design of that bearing plate, right? Just now already shown this, right? The width of that lower story column is equal to 250 mm width of the flange, and its depth is equal to 300 mm. That in plan, I'm showing in plan. This is how that lower story column, whereas for the top story column it is 200 mm. Width of the depth is 200 mm, right? Therefore, now I do have. Now also, what I'm assuming that here the assumption is that the load, right? Let me go to that given data. What is the load given, right? The load that is given is a load of 600 kilonewton is acting on the top story, right? Now I'll assume that is unfactored load, therefore now I'll multiply with a factor of safety of 1.5. Therefore my design load is equal to 900 kilonewton. 900 kilonewton. Therefore if that 900 kilonewton is load is acting, then it is presumed that 450 kilonewton is transferred by this flange, as well as 450 kilonewton is transferred by this another flange on the other side. And similarly these flanges of the bottom story will also receive same 450 plus 450 kilonewton loads. Therefore there is a perpendicular distance between this 450 and 450 kilonewton loads. Therefore I want to find out that which is leading to the bending of this base plate. What is the bending moment of that base plate? I can obtain from that perpendicular distance of these two plates, and hence I am showing that same 450 kilonewton is transferred, and as well as the same is received, right? Therefore there is a load is transferred from the flange, and the equal and opposite reaction, right? 450, therefore leading to the top the bending of this base plate, between this, right, 450 and this 450. Therefore that is how it is bending, right? Hence what is that distance between the two loads, of the top story column, it is equal to 200 minus this thickness of the flange, half the thickness of the flange here, as well as the half the thickness of the flange here. Therefore that now works out 200 minus the thickness of the flange. However, for the top column, it is the thickness of the flange is equal to 9 mm. Therefore this distance is equal to 191 from here to here. It is 191 mm, right? Similarly for the bottom story, it is 300 minus thickness of the flange, this, right? So from center of the flange to from center of the flange is equal to 300 minus one flange thickness 10.6. It now works out, say 289.4, right? Like this, right? From this center to from this center, right? Similarly from this center to from this center, right? Therefore once I get these, right, what is that perpendicular distance between these two forces, which is leading to the bending of this base plate, Therefore now I'll get, therefore the distance of the forces or the eccentricity, both are same, right, is equal to 289.4 for the bottom story minus 191. However that is equally on the two sides, that divided by 2 is equal to 49.2. This gap is equal to 49.2, right? This is the eccentricity between these two forces, right? Therefore hence once I get that eccentricity, hence the bending moment on the bearing plate is equal to M is equal to P multiplied by E, 450 kilonewton multiplied by 49.2 divided by 10 to the power 3, it works out, say 22.14 kilonewton meter. To that much of bending moment this base plate is subjected, right? Therefore once I know that bending moment, therefore I'll go to the equilibrium equation that M is equal to Mr. However the moment of resistance of the section is given by M is equal to Fz, where F is equal to yielding. By yielding criteria, Fi multiplied by Z. However Z is nothing but B multiplied by D. This bending moment is acting over a thickness T. Let the thickness of the base plate is equal to T. Therefore B is the width multiplied by T, Pt square by 6. Therefore equating this to the bending moment 22.14. Therefore I am equating that 22.14 into 10 to the power 6 is equal to, right, Fi is along with a partial safety factor 1.1, or even if I go to this page number 53, let me go to this page number 53, student, right? Page number 53 of IS 800, page number 53, right? Yes, I am there in page number 53. Therefore this is for the design of the beams actually, right, wherein the permissible bending stress is equal to Fi divided by gamma m naught, right? Fi divided by gamma m naught, right? Therefore that is what the permissible bending stress. Therefore this base plate is under bending, therefore this is subjected to a permissible bending stress of Fi divided by gamma m naught, 250 divided by 1.1, that multiplied by 250 multiplied by T square divided by 6. Therefore equating both of these, only unknown is equal to the thickness of the base plate. This thickness of the base plate now works out say 48.35, but the nearest thickness that is available in the market is equal to 50 mm, right? Therefore, provide a bearing plate of 300 mm that I already showed like this, right? 300 mm, right? This is how that the size of the bearing plate, student, 300 mm by 250 mm multiplied by this 50 mm, which is provided here, or let me show like this, right? This is how 300 mm by 250 mm. This is 300 mm. The transverse direction is 250 mm, and this thickness is equal to 50 mm, right? Now, once I can conclude this bearing plate design, let me go to the next design, student, right? Next design is that now I need to design this splice plate, the splice plate on the flange, right? Therefore, now please see that what is given in the problem is that the ends of the columns are made flush by machine cut method. Flush means it is perfect. It is having a perfect contact with the bottom contact plate or the bearing plate perfectly, right? That is what called flush, right? Therefore, 100% load is transferred by the bearing only, but however, we need to design at least 50% of the load need to be transferred by the splice plates and their connections, right? Therefore, now that we already discussed, therefore the load to be transferred by the splice plate is equal to 50% of the load. Therefore, that now works out say 50% of 450 kilonewton, because 450 is acting on each of the 450 kilonewton is transferred by each of this flange. Therefore, now flange itself will transfer to 25 kilonewton. Rest is presumed to be transferred by the splice plate of 225 kilonewton, right? Therefore, that is how only axial load, student. Please make a note that there is only axial load, right? Now, and also let us see this that the width of the splice plate at the top is equal to 200 mm like this, right? Whereas slowly it is increasing to 250 mm at this joint, and there onward it is remaining constant 250 mm. Now I'll show that, right? Like this, right? Therefore, here it is 250 mm increasing to 300 mm, right? This splice plate is equal to width of this width of that flange. I'm sorry, student. Right? The width of that flange plate is equal to 200 mm. However, the width of this bottom column flange is equal to 250. Therefore, 200 slowly increasing to 250 mm at this intersection, right? There onward it is remaining a rectangular, right? That is how the variation, 200 increasing to 250, then 250, right? That is how the section. This I want to design. Therefore, now I'll initiate that design, right? However, all these splice plates must be designed for a slenderness ratio of lambda is equal to 0, right? Slenderness ratio of lambda is equal to 0 means they will not be subjected to any buckling, nor any reduction in the compressive stresses is possible. Therefore, in such a case, as per this class 7.1.2.1, page number 34. Let me go to this page number 34, student, right? Of IS 800, page number 34, right? Yeah, 34. Yes, I am there in page number 34. Just bear for me, right? Therefore, now I am there in the design of compression members, whereas the permissible, the design compressive stress FCD should be, in the worst case, should be less than or equal to Fi divided by gamma m naught, right? Means there is a maximum permissible design compressive stress is Fi divided by gamma m naught. Even the same is also applicable for the bending criteria also, just now we have seen. Hence, the maximum permissible maximum permissible design compressive stress 250 divided by 1.1 which will now work out 227.27. Therefore, the area of this splice plate required is equal to the load transferred by the splice plate is equal to 225 into 10 to the power 3 kilonewton. That would be 227.27. That works out say approximately 991 mm square. Already the width is decided, student, right? The width is varying from 200 mm to 250 mm. However, I'll use 200 mm so that there the design is critical, right? Therefore, less the width, more the thickness required. Therefore, the thickness required, T required is equal to area divided by that width at the minimum width, right? 991 divided by 200 mm, which will work out say 4.96 approximately. If I divide with 250, I'll get less than 4.95. Therefore, that will not govern the design, but that divided with 200 will govern the design. Please make a note of this, student, right? However, the thickness of the plate that is available next thickness is only 6 mm, right? 1 point, right? Or even 5 mm is also available, but if at all these are exposed to open environment, the thickness should not be less than 6 mm. Therefore, I am using 6 mm thick bearing this splice plate as shown in this figure, right? This splice plate design is also over, student. First component was the design of the bearing plate. The second component was the design of this splice plate, right? Now I am left only with the design of these bolted connections connecting the splice plate with that of the flange. Now let me go to that in a quicker pace, because you already seen in the previous problem also. Now I'll do this at a quicker pace, right? Therefore, bolted connections, as design of the bolted connections, because there is a filler plate of 50 mm, very large thickness. Therefore, now I'm assuming a somewhat higher diameter of the bolt, ordinary black bolt, higher diameter, not just 16. I'm assuming 24 mm. Therefore, that is my assumption, assuming 24 mm diameter bolt. However, if I go to this table 73, just now already shown in the previous problem, that for 24 mm, let me go to this table 73. Table 73. Just wait for a moment, right? 73, right? 73. Yes. Therefore, for 24 mm, you can see that, right? The diameter of the standard bolt should be 2 mm only. For larger than 24 mm, this is 3 mm. Therefore, now I am taking this as, say, the diameter of the hole. I am taking as, say, 3 mm. Though I can take 2 mm also, but I am taking 1 mm more, right? Therefore, diameter of the hole is equal to 24 plus 3 is equal to 27 mm. And even as per this class 10.2.2, page number 73, just now we discussed in previous problem that the pitch should not be less than 2.5 multiplied by 24. It works out, say, 60 mm. Or say I want to provide 65 mm. And also the minimum edge distance E is equal to 1.5 multiplied by nominal dia 24 mm. It works out, say, 36 mm or say 40 mm. These are my assumptions, right? And also for 4.6 grade bolt, from IS 1367 part 3, 2002, page number 9, we already shown in the previous problem that A and B, net area of this bolt, is equal to approximately 0.78 multiplied by pi by 4 multiplied to 24 square. It works out, say, 353. And you please see that there is a packing plate, or there is a filler plate required of 50 mm. Therefore, once a filler plate is required, then obviously I need to do a correction, right? Therefore, if I what is the thickness of this packing plate, right, is 50 mm. Therefore, if I go to this class 10.3.3.2, page number 75, let me go to that, right? Let me go to that page number 75 of IS Internet, student, right? Yes, here. Now, what the code says is that the correction is needed for this one long joint, as well as the correction is also required for the large grip, right? Whereas the large grip means if the let me read this, right? If the grip length LG equal to the thickness of the connected plates exceed 5 times the diameter of the bolt, the design shear capacity shall be reduced by BLG, long grip, right? Given by 8D divided by 3D plus LG, right? and BLG shall be more than BLJ as given in class 10.3.3.11. Correction factor may be needed, and the second correction factor that is may be needed is the thickness for the packing plate. Design the shear capacity carrying these shear through these packing plates if at all they exceeds 6 mm. In our case, the thickness of the packing plate is greater than 6 mm because 50 mm is greater than 6 mm. Therefore, the shall be decreased by a factor beta pk. Pk for packing plate given by 1 minus 0.0125 multiplied by tpk. However, even another correction is also required, long joints. However, if the length of the joint LJ exceeds 15 times the diameter of the bolt in the direction of the load, then beta LJ is given by this 1.05 LJ divided by D. LJ divided by D. These three correction factors are needed. Therefore, however, let me see the first correction factor. The first correction factor that is required is for the packing plate. Obviously, I require this because the thickness of the packing plate is more than 6 mm. Therefore, upon substitution, now I'll get 1 minus 0.0125 multiplied by 50. Therefore, this correction factor required is 0.375. However, let me also check the second one. What is the grip length of the bolt? However, the grip length of the bolt is the thickness of the splice plate plus thickness of the splice plate is equal to 6 mm. Thickness of the filler plate. Thickness of the splice plate is equal to 6 mm. Thickness of the filler plate is equal to 50 mm, as well as the thickness of the flange. Thickness of the flange is equal to 9 mm. Therefore, the summation of all these three is equal to 65 mm. 65 mm. However, this is much less than 5 multiplied by diameter 24 to 120. Therefore, no reduction is needed for the large grip. For the large grip, there is no reduction needed for the large grip, right? Therefore, only one correction is needed for the packing plate. For the packing plate only, this much of packing plate only. Therefore, now let me calculate. First, let me calculate what is it shear capacity. Therefore, as per this class 10.3.3, in the previous problem we have seen this from page number 75 that even the bolts are there in single shear. Please make a note. Let me go to this schematic, student, right? Though these bolts are connected from through this splice plate, through this filler plate to this flange plate, all the three are acting as if one unit. Therefore, only they are under single shear only. Please make a note. This is not under double shear, not under triple shear, right? Please make a note, student, right? Hence, this is only under single shear. Hence, the design strength of the bolt in single shear is now given by this, along with the reduction factor. N multiplied by A and B multiplied by FUB divided by root 3 multiplied by gamma MB multiplied by beta PK. Therefore, upon substitution, now it works out. Say a value that divided by 10 to the power 3, it works out say 24.45 because NN is equal to 1 multiplied by A and B is equal to 353 multiplied by 400 divided by root 3 multiplied by 1.25, that divided by 10 to the power 3 multiplied by 0.375. Right, it works out at 24.45 kilonewton. However, even I want to calculate the design capacity of the bolt in bearing criteria. Therefore, for which I need to calculate KB. What is that KB? E divided by 3D naught. However, just now we have seen that this 3D naught is equal to 40 divided by 3 multiplied by 27. It works out say 0.493. Even the second criteria is that P divided by 3 naught minus 0.25. 65 minus 3 multiplied by 27 minus 0.25. It works out say 0.555. The third criteria, FUB divided by FU. 400 divided by 410. It works out say 97.5%. The last one is 100%. Out of all these, the minimum is 49.3%. Therefore, now as per this class 10.3.4 of page number 75, the bearing capacity of the bolt is equal to 2.5 multiplied by this KB, 493 multiplied by diameter of the bolt, 24 multiplied by thickness for the bearing. However, please see that here I do have the three thicknesses, right? One is 6 mm, right? Another is 50 mm, and the third one is 9 mm. Out of all these, this thick 6 mm thick splice plate will fail first in transfer of the load through bearing, through perfect contact, right? Therefore, there is a thickness for the bearing, student, 6 mm, 6 mm, and 6 mm. That multiplied by 400 divided by 1.25, that divided by 10 to the power 3, it works out as 56.8 kilonewtons, right? Therefore, the bolt value is either 24.45 or 56.8. Out of these, 24.45 is the minimum value, right? Is the bolt value. Therefore, the number of bolts that are required is equal to the load transferred by this splice plate is 225 divided by bolt value 24.45. It works out, say, around 9 point odd value, or say 10 number of bolts. Next integer is 10 number of bolts. Therefore, I'll be providing 10 number of bolts. Generally in 2 rows, means in each row I'll be providing 5 bolts. Therefore, 5 number of bolts as well as 5 number of bolts, right? Like this, right? 5 plus 5, 10 number of bolts, right? For the upper story, this is the bolted connection for the upper story we have examined, right? 10 number of bolts, right? Similarly, I'll design the number of bolts that are required for the lower story also, right? Therefore, if I see this, however, here you please see that however the reduction in the shear for the packing plate is not coming into picture because it is already crossed. Therefore, here no such connection is needed. Therefore, the design strength of the bolt in bearing without any correction factor is equal to the 353 multiplied by 1. This is also under single shear, multiplied by 400 divided by root 3 multiplied by 1.25, that divided by 10 to the power 3. It works out, say, 65.21 kilonewton in single shear. However, just now we have seen for the bearing criteria, it worked out 56.8. Therefore, the bolt value is either 65.21 or 56.8. However, in bearing it will govern, which is equal to 56.8. Therefore, the number of bolts that are required is equal to, still the load is transferred is 225 divided by this 56.8. It works out, say, 3 point odd value, or say because we are providing in 2 rows, that should be a multiple of 2. Therefore, r say 4, or even you may say 6, that is left to you. Therefore, I am saying, say, 4 in 2 rows means 2 plus 2. That is how 4 number of bolts are provided, as shown in this figure. Right? That is how the design of the bolted connection, right? Or as shown in this figure, right? Therefore, here I am providing just wait for a moment, right? I am providing for the top plate I am providing 10, and for the bottom plate I am providing 4, right? Like this, right? Therefore, here not I am showing 8, but like that there are 10 for the top column, whereas for the bottom only 2 plus 2, 4 only, right? That is how the design. However, once I do this, the number of what is the depth of this base plate, the splice plate required? That is nothing but this edge distance plus these, right, pitch, and here one edge distance, pitch, right, edge distance, right? Therefore, if I sum up, it now works out, say a value which is equal to say this much, right, which is 5 multiplied by 65, right? Because there are 1, 2, 3, 4, here 1, 5, and there are 1, 2, 3, 4 edge distances of 40 mm, and as well as a base plate of 50 mm thickness is also provided, student. Please make a note. Therefore, plus that, therefore it works out, say, a total value of 535. Hence, provide a splice plate of 535 by 200 increasing to 250 mm with a thickness of 6 mm, right? As shown in this figure, right? This figure, right? 535 with a width of 200 increasing to 250 mm with a thickness of 6 mm provided by means of 10 number of bolts connecting the top column and and 4 number of bolts in the bottom column. I hope you understood this problem, student. Once you understood this problem, now let us move to the top, the third problem, right, wherein the third problem is like this. Let me move to the third problem, right. Is a problem wherein it is subjected to just wait for a moment, right. This is a third problem, right. This third problem is a design of splices for columns, or design of column splices for columns of same cross section subjected to 1 axial force, 2 shear force, and 3 bending moment. All the 3 are there, student. In the previous problem only axial force was there. Now axial force is there, the shear force is there, and the third one is the bending moment is also there, right. Now hence if I see this problem data, right, let us see this problem, right. A column section ISHB 300 at the rate of 680 Newton per meter is subjected to a factored design load of axial load of 450 kilonewton and a shear force of 100 kilonewton and a bending moment of 30 kilonewton meter. Design the splice plate and the bolted connections using same 4.6 grade bolt as well as use Fe410 grade steel, right. I think the data is almost here and there the same data, student, right? This is a given data. I'll not go through it elaborately. Hence for Fe410 grade steel, Fu ultimate stress is equal to 400 and Fi is equal to 250 Newton per meter square, and the partial safety factors we have seen in the previous problem, gamma m naught is equal to 1.1 and 1.25, and also from this IS 800 2007 from table 1 from page number 13, even we have seen that for Fe4 4.6 grade bolts, FUB is equal to 400 Newton per meter square, and partial safety factor for the bolts is equal to 1.25, right. And also from same IS 800 2007 from table 46 of page number 138 for ISHB 300, right. Even just now we have seen from page number 138. Let me go to that page number 138. A quicker page 138, right. Yes, this is page number 138 for ISHB 300. For ISHB 300 at a rate of 618 Newton per meter. 618, right. Yes, 618 means 63 kg per meter. This is how these are the relevant properties. 80.25 centimeter square, and depth of the section is 300 mm, width of the flange is equal to 250 mm, and thickness of the flange is 10.6, and thickness of the web is equal to 9.4. Therefore, I just noted down that relevant properties, right. Here, I have just highlighted that, right. And now I am designing first component as the design of the flange splice plate. Flange splice plate subjected to axial load and bending moment, right. This flange splice plate, right, subjected to a factored axial load of 450 kilonewton and a factored bending moment of 30 kilonewton, right. Now what I'm doing is that I'm assuming the ends of the column as machined for complete bearing, Therefore, if that is the case, then the column ends are flush, obviously, right. The flush, right, like this, right. Hence 50% of the load is transferred directly and 50% by the splices. Therefore, the load on each splice is 50% of the load is 225, that divided by 2, because 2 splices are provided on either side. Therefore, it works out say 112.5 kilonewton. Therefore, the load on the splice due to the movement, even the bending moment is also given 30 kilonewton. That divided by eccentricity. However, what is the eccentricity means? It is the distance between the center to center of these flange plates, which is equal to 300 plus half the thickness of this splice plate and half the thickness of this splice plate, right. Therefore, it works out same 300 plus 6, 306. Therefore, is the perpendicular distance between the two forces. is the eccentricity. Hence, the load on the splice plate will now work out 30 into 10 to the power 3 divided by 306. It works out say 98 kilonewton, very large value, right? You please see that already the splice plate is subjected to an axial force of 112.5, almost roughly the same equal amount of axial load is coming due to just a movement of 30 kilonewton. Though this is a small movement, however, that is giving rise to around equal value here and there, right? Therefore, it cannot be neglected. Therefore, if you neglect this much of force on the splice plate, then obviously it will fail, student. Therefore, that shows the importance of taking into account the movement on the splice plate. Therefore, now I'll sum up. Therefore, the total design load on each splice plate PSU is equal to, from the direct axial load 112.5 and as well as due to the movement 98. Therefore, it works out at 210.5 kilonewton only, right? Hence, the width of this splice plate is already shown. Let me show this schematically, right? This is equal to, not this figure, student, right? Like this, right? Or let me go to this side. This is the problem, right? This width. This is the problem I am doing, student, right? Which is equal to width of the flange of the column, right? However, the columns are both are same. Therefore, now let me note down that width of that column flange is equal to 250. Therefore, this is 250. This is 250, right? Now, also, once I fix that, therefore the area of the splice plate required, area is equal to the load to be transferred by the splice plate PSU divided by Fi. These splice plates should be designed for yielding stress only, right? Therefore, 210 into 10 to the power 3 divided by 250, it works out say 842 mm square. But already width is fixed, therefore the thickness of the splice plate required, T is equal to area divided by width of this splice plate provided, right? 842 divided by 250, it works out say 3.37. However, the thickness in any case should not less than 6 mm. Therefore, R says 6 mm because if they are exposed to open environment, then 6 mm is the minimum thickness that is required. Therefore, let us provide 6 mm thickness. But now let us see next subheading as the design of the bolted connections, right? Design of the bolted connection between the flange and the splice plate. Flange and the splice plate. This one, right? Just now we have designed this. Therefore, I am trying to design these bolts. How many number of bolts are required on either side of the joint? This is how the joint, student, right? These number of bolts are required, right? Therefore, now let me do that design. Right? I am assuming 16 mm dia bolts. Therefore, from the previous problem, let me go to the previous problem, right? Just now discussed, right? In the previous problem that bolted connections, yes, right? Therefore, from class 10 point R, let me go to this data also, right? Here I already assumed 16 mm dia bolt. Therefore, for 4.6 grade bolts, FUB is equal to 400 Newton per mm square from page 13. As well as the partial safety factor for the bolt, gamma MB is equal to 1.25, and just now we assume the diameter of the bolt as 16 mm. Therefore, from this page 73, let me go to the page number 73. Wait for a moment, right? 73, right? Yes, from this 73, for 16 mm dia bolts, the diameter of the hole should be 2 mm extra. Therefore, 16 plus 8, it works out say 18 mm. Therefore, that is what I am having. DH is equal to 18, and from 1367 part 3 table 6 page number 9, the net area of the bolt you can note down, or alternatively let me go to that page number 9 of 1367, right? For M16 bolt, it is 157. Or alternatively, what you can do is you can also find out equal to 0.78 pi by 4 16 square, it works out say 157. Therefore for that from this class 10.3.3 page number 75, let me go to the page number 75. This is how from page number 75. Yes, right. Therefore I do have the shear capacity of the bolt VD SB is equal to Vn SB divided by gamma MB, where Vn SB is equal to Fu divided by root 3 Nn multiplied by A and B, and also as per this class 10.3.4 bearing capacity of the bolt VD PB is equal to Vn PB divided by gamma MB, where Vn PB is equal to 2.5 kb dt Fu. Kb is equal to least of the 4 E divided by 3 naught, P divided by 3 naught minus 0.25, FUB divided by FU, and fourth one is 1. Therefore, from this now I'll calculate the design strength of the bolt in single shear. Obviously, you please see this figure that there is only single shear. The bolt is subjected to only single shear because this is how in between only this is how a single shear to which the bolt is subjected to, right? Hence the value will now work out a result say 157 multiplied by 1 single shear multiplied by 400 divided by root 3 multiplied by 1.25 divided by 10 power 3, say 29 kilonewtons. However, as per this class 10.2.2 page number 73, let me go to the page number 73 student at a quicker pace. 73, just now also we have seen 73. Yeah. Yes, right. I would have the minimum pitch. The pitch of the bolt should not less than 2.5 times the nominal diameter of the hole, and even for the compression member, the maximum pitch is not more than 20 or 200 mm, and as well as the edge distance from class 10.2.4.2 shall be 1.5 times the hole diameter in case of the rolled machine flame cut method, right? Therefore, using these, now I'll calculate the pitch shall not less than 2.5 multiplied by 60 mm or say 40 mm, and the maximum pitch 12 multiplied by 6 because the splice plate is equal to 6 mm thick. Therefore, either that 6 mm thick or that of the flange plate, whichever is minimum. Out of these two, flange plate will fail first. Therefore, 6 mm will govern the result. 12 multiplied by 6, 72 or 200 mm, whichever is minimum, 72 will govern the result. Therefore, let us fix the pitch as 50, which is in between 40 and 72. Okay. And also, as per this class 10.2.4, the edge distance should not less than 1.5 times the diameter of the hole, 18, say 27 mm or say 30 mm, right? 30 mm. Therefore, once I do that, now I'll find out this kb value. Just now gone through those code specification. E divided by 3 naught, it works out say 30 divided by 3 multiplied by 18, say 0.55 from first criteria. The second criteria, P divided by 3 naught minus 0.25, 50 divided by 3 multiplied by 18 minus 0.25 is equal to 0.676. The third criteria is Fu divided by Fu, 400 divided by 410, which is 0.975, and the fourth criteria is 1. Therefore, out of all these, 0.555 is the least one. Therefore, the design bearing strength of the bolt VDPP is equal to 2.5 kb dt Fu divided by gamma mb. Substituting the numeric values, now I get say 2.5 multiplied by 0.555. Diameter of the bolt is 16, and the thickness for the bearing, just now already told that 6 mm will fail first. 6 mm will fail first. That multiplied by 400 divided by 1.25 divided by 10 power 3, it works out say 42.62. Therefore, the bolt value is 29 kilonewton only. 29 kilonewton only. Therefore, once I fix the bolt value, now I'll go to the number of bolts that are required. Therefore, that is how just fixed the bolt value, student. That is how this bolt value is fixed as 29 kilonewton, right? Bolt value is fixed as 29 kilonewton, right? Therefore, the number of bolts that are required, the load to be transferred by the splice plate is equal to PSU divided by bolt value. 210 divided by 29, it works out say 7.26 or say 8 number of bolts. 8 number of bolts need to be provided. 8 number of bolts need to be provided as shown in the figure. Now I'll show in 2 rows. Therefore, 4 plus 4, 8 number of bolts on either side of the joint, right? Therefore 8 here on the top story as well as the bottom story of this column also. Actually this is not a story but a joint, actually a splice, right? Therefore on the top of this joint or splice, on the bottom of this joint also 8 on either side, right? Therefore these are 8 and these are also 8 and these are also 8, right? Therefore that is how I just fixed the number of bolts, and even just now we have seen that the edge distance is equal to 30 and each pitch is equal to 50 50 50, and also at the end the edge distance is equal to 30. Therefore now I'll fix what is that depth, the depth of the splice plate provided. H is equal to, there are six pitches of 50 mm, right, and 4 edge distances of 30 mm. Therefore the depth of the splice plate provided is equal to 420. This is what 420, or this is also 420. This depth is also 420. Okay, that is how the, or let me show in the schematic, right? This is how 420 is the depth. 420 is the depth, and these are 8 number of bolts, right? Actually here they are provided in 2 rows, 2 plus 2 4 rows, but I am providing only in 2 rows, right? Therefore 1 2 3 4 and 1 2 3 4 in 2 rows, right? That is how the design of the bolted connection as well as the splice plate is now concluded. Now once I conclude that, now what I'll do as shown in the figure, is provide a splice plate of 420 by 250 by 6 mm splice on the column flanges connected by means of 8 16 mm dia ordinary black bolts in 2 rows as shown in the figure, right? Like this, right? As shown in this figure schematic, right? Or this part along with these pits as well as these edge distances to a depth of 420, and this width is equal to 250 only with a thickness of 6 mm only. This thickness 6 mm. That is all the design of the first component along with the bolted connection. Now I'll go to the design of the second component, student, right? You please see that we have so far we have designed for axial force as well as bending moment. Now what is now left is the shear force. A horizontal or transfer shear of 100 kN is there. Therefore I need to design the web splice plate for a shear force of 100 kN. Before that, what I need to do is that I need to design these bolted connections between this web and splice plate. Just now we have noted that pitch is equal to 50 mm and edge distance is equal to 30 mm. Therefore, assuming a pair of the splice plates on each side of the web and assuming a diameter of the bolt is equal to 16 mm. Let me show what is the pair of the pair. Means here one plate as well as on the other side of that web another plate like this, right? Another plate, right? A pair on back to back and back to back, right? That is how we will be generally providing. That is what called a pair, right? I hope you understood this, right? Therefore and diameter of the bolt is equal to 16 mm. Therefore just now we have seen, however, because I am providing a pair, right? Obviously this is also a web is also there, web is also there. Hence if I provide a bolt, that will be there in double shear. Therefore this is how one shear plane as well as another shear plane, that the bolts are there in double shear. Hence these bolts will be there in double shear. Hence the strength of the bolt in double shear is equal to, right, already we obtained in the above heading as the strength of the bolt in single shear as 29. Therefore the strength of the bolt in double shear is equal to 2 multiplied by 29, 58 kilonewton. And here also I am assuming this thickness of this splice plate, that of the web splice plate, is equal to 6 mm. Therefore the thickness for the bearing is equal to, there are the two splice plates, therefore total thickness is equal to 12 mm or the thickness of the web, this thickness of the web, right? These two thicknesses are 6 plus 6, 12 mm, or that of this web of 9.4, whichever is minimum. Therefore what governs the design is this 9.4 plate will fail first, web will fail first. Therefore, the thickness for the bearing is equal to 9.4. I hope you understood how I am getting the thickness for the bearing. For bearing is equal to 9.4. Therefore, the design strength of the bolt in bearing VDPB is equal to 2.5 multiplied by 0.555. We already obtained in the previous subheading, right? KB is equal to 0.55 multiplied by diameter of the bolt is equal to 16 mm, and thickness for the bearing is equal to 9.4 multiplied by 400 multiplied by divided by 1.25 divided by 10 to the power 3. It works out as 66.78. Therefore, the bolt value is the least of the two is equal to 58 or 66.78. Therefore, B is equal to 58. Hence, the number of bolts that are required, N required, is equal to the transverse shear, the horizontal shear, right? This transverse shear, right, of 100 kilonewton, which is acting on this splice plate, right, divided by the bolt value 58. Therefore, that now works out, say a value 100 divided by 58, 1.78, or say 2. However, generally we will be providing in one row only. Therefore, I'll provide two bolts like this, right? Therefore, that is how I'll provide, right, 2 bolts in one row only, right, at an edge distance of 30 mm as well as at a pitch of 50 mm, right? Therefore, the width of this plate provided is equal to 50 plus 30 plus 30, 110 mm, right? That I have already fixed. And also, the depth of this splice plate provided is equal to now I do have here one edge distance 30 mm, another edge distance 30 mm, right? Therefore, two edge distances as well as two edge distances. Therefore, 4 multiplied by 30. Therefore, the depth of this splice plate required is equal to 120 mm. Therefore, I have fixed the depth also, right? That is how I just now fixed, right, the depth, right? And so now I'll go to the design of this web splice plate subjected to the shear force, right? Whereas this is subjected to a shear force VU is equal to 100. However, in strength of material, we learned that the I section, the shear stress across the I section is not uniform, right? At the intersection, right, it is the minimum in the flanges. However, the intersection of the flange with the web, it escalates and it increases parabolically to a maximum value at the CG of this I section, a maximum value. Therefore, there is a non-uniform distribution of the shear stress. Therefore, now I'll from that strength of material variation of the shear force, now say that the design shear force, right, the maximum design shear force is equal to 1.5 times the average shear force. Therefore, already average shear force that itself is design actually, but at the central axis of the web or this column section, I am assuming it has 1.5 multiplied by that 100 kilonewton. Therefore, I am designing for 150 kilonewton, not just for 100. Though, even though that is the factored shear of 100 mm, I am increasing by 50% for non-uniform distribution of the shear stress across the cross section of the I section. Therefore, I have fixed 150 mm. Therefore, the width of the splice plate just now I have shown, right, is equal to 110 mm. This I have already shown schematically, right? This 110 mm I have already shown, right? And once I get this, now let me calculate, right? What is the design shear strength of this splice? Is equal to, numerically is equal to Fu divided by root 3 divided by gamma m naught multiplied by this splice plate width is equal to Bs multiplied by, there are two splice plates. Therefore, 2 multiplied by Ts is the design shear strength of the splice plate. A pair of the splice plates. Please make a note, student. A pair of the splice plate, right? However, this should be greater than or equal to the shear to which these are subjected, 150, right? Therefore, now I do have 250 divided by root 3 divided by 1.1 multiplied by 110 width just now fixed multiplied by two thicknesses of the splice plates, 2 TS should be greater than or equal to 150 multiplied by 10 to the power 3. That for solving it, now I'll get thickness should be greater than or equal to 5.19. But however, R says 6 mm, right? Should not be less than 6 mm, right? Therefore, I am providing each splice plate of 6 mm thick. Therefore, the depth of the splice plate required, just now already told that 4 such end distances are needed. 4 end distances, right? 1, 2, 3, 4. Therefore, 120 mm depth is needed. Hence, provide a splice plate of size 120 depth, 110 wide, right? 120 depth, 110 wide, and a thickness of 6 mm on either side of the web as shown in this figure, connected by means of 2 bolts on either side of the splice, right? 2 here and as well as 2 here as shown in this figure. That is how the design. Or let me show that in this schematic, right? Like this, right? This web splice, right? Or let me also show the aerial photograph like this, right? Therefore, 2 plus 2 4. This is the web splice, as well as this is the flange splice. This flange splice is subjected to the axial forces as well as the bending moment, whereas this web splice is subjected to the transfer shear, right? That is how the design of a splice subjected to 1 axial force, 2 bending moment, as well as the transfer shear, right? That is how the design student. That is how the designs what we have discussed in today's class, right? Therefore, I hope you enjoyed the discussion what we discussed in today's class. If you have really enjoyed, right, don't forget to subscribe, like, comment, and share to our YouTube channel. In the next class, we shall see the design of column bases, design of slab bases, as well as the gazetted bases. Few problems, right? Till then, bye bye, students.